Hello guys, welcome back to the channel. I'm going to start a series of talks talking about writing an operating system in Rust. We all know that Rust is a systems programming language. It can be used for writing embedded systems code, drivers, and I was very curious to see uh, writing an OS in Rust. So I am following this blog, and in each day, on each day, I am going to walk you through each of the blog posts. So these there are, I think, 13 or 14 blogs, and with each blog we are going to write an operating system in completely in Rust. And for that, for demonstrating that, I am going to use a Raspberry Pi. We are going to write an operating system for Raspberry Pi, and see how can we write an OS in completely in Rust. So let's start with a very basic thing. What is a freestanding Rust binary? Now, this freestanding Rust binary is nothing but a binary which is not linked with an operating system. So whenever we write our first Rust code, it basically by default links with our standard library. Now, standard library feature is a part of operating system, but since we are writing our own operating system, we need to first start with getting rid of the standard library features. So in order for that, the very first thing is disabling the standard library. Basically, we can just create a. So currently, I have given it my program name as Rust OS, and I have added this particular macro. So this no standard macro, whenever we define this no standard macro, it basically says that there is no standard library feature available now. So now if we try to add print ln macro over here, Rust analyzer will throw an error that he is not able to find the println macro. So that means that our standard library is not added to our main code. The next thing we need to do is getting the panic handler working. Now, panic handler is nothing but it is a feature of your standard library, which basically gives you the functionality to handle panics in your code. So now, since we don't have a standard library, we need to define our own panic handler. And here's the way to define a very simple panic handler. We can just import panic info struct from core library. So if we go into panic info, let's see what is there in panic info. Okay, I need to enable it, panic info, and we'll go inside it. So this is a struct which is being defined in core library, and it has message, location, can unwind, and force to backtrace some of the parameters of that struct. So what our panic handler does is it goes into an infinite loop, nothing else. And for the sake of simplicity, we are not doing any extra stuff. We are just going into an infinite loop whenever the panic occurs. Now this is one thing, but what happens with the stack when the panic occurs? So that thing, or that is taken care by personality language item. Now this language item takes care of unwinding your stack from the point where panic occurs to calling the function which has called the function where panic has occurred, and then releasing the stack and releasing all the variables from this from the stack. Basically, what we say, it clears off your stack and then gives the information to the user that gives the information to the user from where that particular panic has been occurred. So this all is being taken care by your OS specific libraries. For example, libu unwind on the Linux, or structured exception handling on Windows. So now, since we are the creator of operating system here, so we need to define our own unwinding libraries. So in order to get started, and for the sake of simplicity, what we are going to do, we are disabling the unwinding. So what he says, you can disable unwinding by using these two, or these two features in your cargo.toml. So what you can do is just go to cargo.toml and enable these two features, wherein we are saying that for development profile and for the release profile, the panic behavior should abort. You should just abort the program whenever panic occurs. And now let's try to build our code, what actually happens. So we say cargo build and release. So we are getting an error, but even before that I want to show you this error. So it is saying use hashbang no main to bypass the Rust generated entry point. Now we all know that we must have an entry point in our program. So there must be a main function in our program, and calling that main function is the task of your start attribute, which is being defined in your C runtime or the runtime system. So basically I come from C programming language background, so that's why C runtimes. So what he says here is the start attribute is responsible for calling your main function. Now since we have disabled our standard library feature, we don't have any start attribute. And what Rust uses C's runtime system, and C runtime system uses CRT0, that is C runtime 0, which sets up the environment for the C application. And this same runtime system is being used by Rust runtime with some added wrapper around it, so that our main function from the Rust binary or Rust program gets called. So now since we don't have the standard library and we don't have this runtime, we need to define a start entry point. Now in order to define that entry point, what we are going to do is we are going to define a C function underscore start. So this I have defined it over here. Let's define our start entry point, and we are doing nothing over here. We are just entering into an infinite loop, and we also need to enable this no main macro. So once we enable this, main goes out of the scope, so we can disable main function. And now let's try to compile our code. Now we are getting a linker error, that is it is not able to link our program, because by default our system tries to compile our code for the host operating system or the host architecture. So in this case it is trying to compile for the Mac OS, but since we are going to, our target is Raspberry Pi, we need to compile our binary for this particular architecture, that is ARM architecture. So that is ARC64 architecture. So let's see. Let's first of all compile it for ARM architecture. So for that, I can just clear the screen. So and once we specify our own architecture, our own linker script needs to be used for. But for the simplicity sake, as this is very first blog, we are not adding any linker scripts and so things like that. So here in this blog, he talks about adding support or writing your operating system for x86 64 unknown Linux GNU architecture. But in this talk or in this series, we are going to write an operating system for ARM A64 architecture. So that will be the only difference with this particular blog and our video streams or videos what I'm going to create. So in order to compile, what he's saying that we can just compile by giving the target. So just take this thing and we'll paste it over here. So what we are saying over here, we are basically cross compiling for this particular target, thumb v7 none eabihf. And if we build this, then we can see that yes, we have got the release working, and debug build also is available. Okay, not here, but here. So this is the debug version of our Rust OS. This is the very first binary which does nothing, but it goes into an infinite loop for this particular architecture. Okay, Now, what is the summary? Summary is this is our code. So we talked about the no standard macro, the hashbang no main thing. Then we talked about panic handler. Finally, we need an entry point for our binary, and at last we need an cross compiled target, or the target for cross compilation. So since I'm using Raspberry Pi, I will compile it for ARM architecture. So that also we have done. And let's see what is there next is. So in the next post, we will talk about creating our minimal Rust kernel, and how can we add a 64. Basically, we will talk about the booting process. So till then, thank you very much for watching. See you in the next video.